Hello, and welcome back to sleep gravity. Rather than beginning in a cloud and ending on the ground, this phenomenon is thought to unfold in an entirely different environment. There is no horizon, no surface from which to watch, and no familiar open space through which drops of water might fall. Deep inside two planets in the outer reaches of the solar system, matter exists under conditions so extreme that familiar ideas about weather almost lose their meaning. And it is there that a very unusual kind of rain may be forming, quietly taking place in absolute darkness, without leaving any direct sign for observers on the outside. If this rain is truly occurring, it begins in a region that sunlight has never reached. There, matter is compressed under pressures so immense that familiar molecules can lose the structures that keep them stable under ordinary conditions. Methane, a compound made of carbon and hydrogen, may no longer remain the kind of gas we know on Earth. Its internal bonds can break apart, allowing carbon to separate, encounter other carbon atoms, and gradually arrange itself into a new structure. Within the right range of pressure, temperature, and composition, that new structure may be diamond. The phrase diamond rain easily brings to mind transparent stones falling through a dark sky, flashing with reflected light before gathering into a bright layer around the planet's center. Science does not yet allow us to go that far. The first crystals would probably be far smaller than any gemstone set into jewelry, perhaps consisting only of carbon lattices measured on the nanometer scale, forming within a hot, dense mixture that ordinary intuition can scarcely picture. In this case, the word rain does not describe droplets falling freely through the air. It is closer to a process of precipitation, in which carbon separates from the surrounding mixture, crystallizes, and then moves toward deeper regions because diamond is denser than the fluid around it. That motion may be slow and continuous, shaped by currents within the planet, where everything is influenced by heat, gravity, and pressure on a scale far beyond anything found in a laboratory. No instrument has ever recorded this process directly inside Uranus or Neptune. The deep layers where diamonds may form lie beyond the reach of telescopes, while also being too distant and too extreme for any present-day probe to enter and continue transmitting data. For that reason, this rain is not known from a photograph or an on-site measurement. Instead, it has gradually taken shape in scientific understanding through a combination of physical models, high-pressure chemistry, and experiments carried out on Earth. In those experiments, extremely small samples containing carbon and hydrogen are subjected to intense compression and heating. Some samples also include oxygen or water in order to better reflect the complex mixtures that may exist inside the ice giants. By observing the structure of matter with ultra-fast X-ray pulses, researchers have found evidence that carbon can indeed crystallize into tiny diamond particles under conditions relevant to the deep interiors of these planets. These results show that the necessary process does not conflict with the known laws of physics. Carbon can separate from its original compound and enter the crystal lattice of diamond when the surrounding environment reaches the right conditions. Yet, what happens inside a tiny sample for an extremely brief moment cannot be treated as a complete replica of a planet that has evolved over billions of years. Inside a real world, chemical composition is uneven, temperature and pressure change with depth. Convection continuously transports material, and crystals may keep growing, dissolve again, or transform into another state after they form. Diamond rain therefore occupies a special place between what has been demonstrated and what must still be inferred. The formation of diamond from carbon-rich material under high pressure has been observed in the laboratory, but the depth at which the process begins inside each planet, the amount of carbon involved, the size the crystals may reach, and the path they follow through the interior are still uncertain. Science has not seen the rain itself, but it has identified the conditions that could allow it to exist. It is this distance between the evidence and the unknown that gives the phenomenon meaning beyond the beauty of its unusual image. It shows that familiar elements do not keep the same form in every world. Carbon can exist in the atmosphere as methane, become part of more complex compounds, and then, under enough pressure, transform into one of the hardest and most stable structures nature can create. A gas in the outer layers may provide the raw material for crystals sinking through the darkness below, while the entire process remains hidden behind clouds that humanity can observe only from afar. The story of diamond rain, then, does not begin with gemstones. It begins with two planets whose matter lies mostly beyond direct sight. To understand why carbon may crystallize there, we must first understand the environment these worlds inhabit, how closely they resemble one another, and why what appears in their outer layers reveals only a very small part of what lies within. From such a distance, Uranus and Neptune remain little more than two dim blue disks, drifting along their vast orbits around the Sunday. They have not revealed the rain, nor shown us the depth at which it begins. Yet behind that quiet blue color lies a realm of matter, where methane may lose its familiar form, carbon may find a new structure, and tiny crystals may have been silently sinking for ages, long before humanity ever knew that these two planets existed. Far out in the solar system, where sunlight has grown far weaker than it is in the space around Earth, Uranus and Neptune travel along two vast orbits. They are not close together in the way a typical illustration might suggest. An enormous gulf still separates their paths, and from those distances, the Sun provides only a small fraction of the energy that reaches Earth. Uranus is the seventh planet from the Sunday. Its average distance is about 19 times greater than the distance between Earth and the Sun, and it takes nearly 84 years to complete a single orbit. Farther out lies Neptune, at an average distance almost 30 times that of Earth. A year there lasts about 165 Earth years, so long that since the planet was discovered in 1846, it has completed only a little more than one journey around the Sunday. The rhythm of the seasons in this distant region unfolds on a very different timescale. On Uranus, each season lasts more than 2 decades. On Neptune, a single season can span nearly half a human lifetime. Sunlight changes very slowly, while processes deep within the planets continue according to their own rhythms of heat, gravity, and matter, almost independent of the faint changes taking place above. Seen from a distance, the two planets appear to be a pair of closely related worlds. Both are roughly 4 times the diameter of Earth. Their outer atmospheres consist mainly of hydrogen and helium, along with a small amount of methane. Methane absorbs part of the red light in sunlight, allowing more blue light to reflect back into space and helping give both planets their distinctive color. Yet that blue tone is not determined by a single gas alone. Layers of haze, cloud particles, and the way methane is distributed with altitude also shape the appearance we see from afar. For many years, widely circulated images made Neptune appear far deeper blue than Uranus. Part of that difference came from the way Voyager 2 images were processed to make clouds, storms, and other atmospheric features easier to see, since many of them were difficult to distinguish in the original data. When observations are adjusted to more closely represent natural color, the two worlds appear much more similar: pale blue, cold spheres covered by thick atmospheres, not identical, but not as dramatically different as many earlier images suggested. Despite their similarities in size and color, they are not copies of one another. Uranus is slightly larger in diameter, but has less mass. Neptune is somewhat smaller, yet heavier, and it has the highest average density of any giant planet in the solar system. This difference suggests that material is not distributed in exactly the same way inside them. One world may contain a greater proportion of heavy material, or its deeper layers may be more tightly compressed, even though both present the same quiet range of color on the outside. Uranus is also unusual because its axis is tilted by nearly 98 degrees relative to the plane of its orbit, making the planet appear to roll on its side as it travels around the Sunday. During part of its orbit, One pole can face the sun for many years, while the other remains in prolonged darkness. This extraordinary orientation may be a trace of a turbulent history, perhaps involving major collisions in the distant past, although its exact cause has not been fully resolved. When Voyager 2 passed Uranus in January 1986, the planet appeared relatively uniform in color and revealed only a small number of clearly visible clouds. That image once led people to regard it as a comparatively quiet world. Later, observations made over longer periods with telescopes showed that its atmosphere still contains winds, clouds, and seasonal changes. The stillness Voyager observed may simply have reflected a particular moment in a cycle lasting many decades, rather than a permanent condition across the entire planet. Neptune displays a much more vigorous pattern of weather. Although it receives less solar energy than any other major planet, its atmosphere still sustains winds that can exceed 2,000 kilometers per hour. Clouds of frozen methane are swept across darker atmospheric regions, forming and disappearing over relatively short periods. When Voyager 2 approached in August 1989, it recorded a vast dark region surrounded by bright clouds. That dark feature later vanished, while new structures appeared elsewhere, revealing that this distant world is far from motionless. Some of this activity is sustained by heat rising from Neptune's interior. The planet not only absorbs energy from the sun, but also releases a significant amount of heat from within. Uranus also possesses internal heat, but the flow of energy escaping from it is far weaker. This difference remains one of the most difficult questions raised by comparisons between the two ice giants. If their sizes and overall compositions are fairly similar, why does one world continue to transport heat outward relatively efficiently, while the other seems to retain much of its energy in deeper layers? The answer may lie in the separate history of each planet. An ancient collision may have altered both the axial tilt and the thermal structure of Uranus. Stable layers of material may also have formed inside it, restricting convection and making it harder for heat to rise. Neptune's interior, meanwhile, may still transport energy more effectively. No single model currently explains all of the available evidence, because humanity has never directly observed what is happening beneath the clouds. Most of our closest knowledge of these two worlds still comes from a single spacecraft. Voyager 2 left Earth in 1977, originally on a mission to explore Jupiter and Saturn. With a carefully calculated trajectory and the help of a rare alignment among the giant planets, the spacecraft continued onward to Uranus in 1986 and then Neptune in 1989. To this day, no other spacecraft has repeated those two encounters. Voyager 2 did not enter orbit around either planet. It simply flew past, collecting data as the distance changed rapidly. At Uranus, the period of close-range study lasted only a few hours. 3.5 years later, the Neptune flyby also provided only a brief window of observation before the spacecraft continued beyond the planetary region. Voyager's instruments measured the atmospheres, magnetic fields, charged particles, rings, and moons, but those data still represent only a short glimpse of two systems that have existed for billions of years. Telescopes on Earth and in space have since been able to monitor their clouds, seasons, and changing colors over much longer periods, but their interiors remain invisible. Light carries information only from the upper atmospheric layers. Their gravitational fields, magnetic fields, and outward flow of heat offer indirect clues, allowing scientists to construct different models of the matter hidden far below. The quiet blue color is therefore only the first layer of the story. Beneath the hydrogen and helium-rich atmospheres, there is no clearly defined ground where a spacecraft could land. With increasing depth, the gases gradually become denser, hotter, and more strongly compressed, eventually blending into regions of fluid with properties very different from familiar forms of matter on Earth. Most of the mass of both Uranus and Neptune lies within these deep regions, where water, methane, and ammonia no longer exist as ordinary gases, liquids, or ice. There, Methane is no longer simply a compound that helps create the blue color of the outer atmosphere. Under steadily increasing pressure, its structure may change. The bonds between carbon and hydrogen can break apart, allowing the atoms to begin arranging themselves along new pathways. Before following the process that may lead to the formation of diamonds, we first need to understand why these two worlds are called ice giants, even though most of their interiors are not made of cold blocks of ice at all. The term ice giant can easily suggest an image very different from reality. When we hear the word ice, we usually think of something cold, solid, and almost motionless, like a frozen lake in winter or an iceberg drifting across the ocean. Applied to Uranus and Neptune, that image might make them seem like enormous frozen spheres, wrapped in gas and filled with a cold mass of solid water deep inside. But in planetary science, the word ice does not describe the present state of most of their material. It refers first to the kinds of compounds being discussed. Water, methane, and ammonia can all freeze in sufficiently cold regions of space, which is why they belong to a group of materials scientists often call ices or volatiles. The term comes from the way these compounds appear in cold clouds, comets, moons, and the distant regions of the disk from which the planets once formed. It helps distinguish them from two other major categories of planetary material: light gases, mainly hydrogen and helium, and heavier substances such as rock and metal. When Uranus and Neptune are called ice giants, the name emphasizes that they contain a much larger proportion of compounds like water, methane, and ammonia than Jupiter and Saturn do. It does not mean that they are made of a cold block of ice in the familiar sense. The reality beneath their outermost clouds is almost the opposite. The deeper we go, the more strongly the weight of the material above presses downward, while the temperature steadily rises. The region often described as rich in ice may reach temperatures of thousands of degrees, yet water and other compounds do not simply boil away as they would inside a container on Earth. The surrounding pressure is far too great. It holds them in dense states that everyday life never gives us a chance to encounter, where a substance can be far hotter than its ordinary boiling point without becoming a thin, diffuse gas. Under conditions at Earth's surface, we usually divide matter into three fairly distinct states. Ice is solid, water is liquid, and water vapor is gas. Change the temperature or pressure enough, and one state crosses a recognizable boundary into another. But when both temperature and pressure rise into extreme ranges, those divisions become less intuitive. A gas can be compressed until its density approaches that of a liquid, while a liquid can develop electrical and structural properties that ordinary water does not possess. In some regions, the clear boundary between gas and liquid can disappear altogether, leaving behind a supercritical fluid that can flow like a liquid while spreading in ways that resemble a gas. So, if it were possible to descend into Uranus or Neptune, there would be no simple moment when the atmosphere ended and an ocean began. The hydrogen, helium, and methane in the outer layers would gradually become hotter and denser, blending into the deeper regions over an enormous distance. Density would continue to increase, the chemical composition would change, and molecules would begin reacting differently as pressure forced them closer together. A descending spacecraft would find no ocean surface to break through and no rocky ground just beneath the clouds. It would encounter only an environment growing steadily thicker and hotter until it became harsh enough to destroy any instrument built from ordinary materials. To describe these interiors, many traditional diagrams divide each planet into three broad regions. On the outside is a gaseous envelope, rich in hydrogen and helium, mixed with methane and smaller amounts of other substances. Beneath it lies the thickest region, often described as a hot, dense fluid layer rich in water, methane, and ammonia. Closer to the center is a region containing a greater proportion of rock, metal, and other heavy elements, usually referred to simply as the core. This division is useful because it shows the general transition from lighter material on the outside to heavier material within. while also helping explain why both planets contain far more mass than a gaseous atmosphere alone could account for. Yet the boundaries drawn so neatly in books and illustrations may not exist so clearly inside the real planets. Their interiors may not consist of three separate layers like the shell, white, and yolk of an egg. Instead, they may contain a sequence of transition zones where composition changes gradually with depth. Water may mix with ammonia, methane, hydrogen, and other reaction products. Rocky material may also be distributed across a wider region, rather than being confined entirely to a small core. The same observed mass and radius can sometimes be explained by several different models, ranging from a planet relatively rich in water to one containing more rock arranged and compressed in another way. This uncertainty does not mean the models are arbitrary. It exists because the measurements available from outside are still too limited to reconstruct one unique interior. Mass tells us the total amount of material. Radius tells us how much space it occupies. The gravitational field offers clues about how strongly that material is concentrated toward the center. Yet many different mixtures can produce nearly the same values. Without precise gravity measurements from a spacecraft orbiting each planet for a long period, along with better information about atmospheric composition and the behavior of matter under extreme pressure, every diagram of the interior remains one possible structure, consistent with the available evidence. Even water, the most familiar member of the group called ices, may exist in unfamiliar forms under planetary interior conditions. Within a certain range of pressure and temperature, water molecules may no longer move as they do in an ordinary liquid. Oxygen atoms can arrange themselves into a relatively stable lattice, while hydrogen nuclei move through that lattice with much greater freedom, creating a state known as superionic water. It carries some of the order of a solid, while allowing hydrogen to move in a fluid-like way, so it does not fit completely into any of the familiar states we normally use to describe water. Experiments that compress water with shock waves have found evidence of superionic electrical behavior under conditions related to the deep interiors of large planets. These results show that a state once known only through calculations can appear in real matter. But they do not mean that the entire interior layer of Uranus or Neptune is made of one uniform mass of superionic water. The water there is mixed with many other compounds, and each ingredient can alter phase boundaries, electrical conductivity, and the way heat moves through the material. One region may contain a large amount of ionized fluid, another may contain superionic water, while hotter areas or regions with different compositions may exist as electrically conductive liquids. This diversity is what makes the word ice both useful and potentially misleading. It refers to the materials that may have taken part in the formation of these planets, but it cannot by itself describe the matter that exists deep inside them today. Compounds that once froze in the cold outer regions of the disk around the sun were gathered together by gravity, accumulated into worlds many times more massive than Earth, and were then compressed and heated by the planet's own weight. Over billions of years, that material ceased to resemble the original grains of ice, even though the historical name remained. Uranus and Neptune should therefore not be imagined as cold spheres from cloud tops to core. Their outer layers are indeed extremely cold, because sunlight has weakened after its long journey through space. But the deep interiors retain a considerable amount of heat and endure pressures far beyond any natural environment found at Earth's surface. Within the same planet, the intense cold of the upper clouds can rest above a hot, dense, and constantly moving world of matter. With these seemingly opposite conditions, connected by a transition extending across thousands of kilometers. This is the region through which the story of diamonds must eventually pass. Carbon would not crystallize inside a motionless block of ice, but within an environment made of many mixed fluids, where temperatures are high enough to break chemical bonds and pressure is strong enough to create new structures. Before reaching those conditions, the journey must still pass through the clouds and the deep atmosphere, following the fading light as temperature, density, and pressure all rise together. Only after leaving the cold appearance of the outer layers far behind can we begin to understand how a planet called an ice giant might become a place where diamonds form in the dark. Once we stop imagining Uranus and Neptune as frozen spheres, cold from the outside all the way to their centers, their blue color begins to take on a different meaning. It is not the color of a surface beneath the atmosphere, nor is it light reflected from a blue ocean covering the planet. Most of what telescopes detect has passed through layers of gas, haze, and cloud above, then returned to space after certain wavelengths were absorbed. The blue color, therefore, does not reveal a clear landscape below. It is more like a veil that allows only part of the light to escape. Sunlight contains many wavelengths that the human eye perceives as different colors. When they enter the atmospheres of these two planets, methane absorbs more strongly in the red and near-infrared regions, leaving the light that returns to space weighted more toward green and blue. This mechanism explains the general coloring shared by both worlds, but it is not the whole story. Haze particles, the thickness of atmospheric layers, the size of cloud particles, and the distribution of methane with altitude can all make the color appear paler, deeper, or slightly different from one region of the same planet to another. The light visible to us therefore probes only a relatively shallow distance. It passes through the thin upper layers of gas, scatters many times, and reflects from clouds and aerosol particles before it has a chance to travel any deeper. At wavelengths where methane absorbs strongly, only clouds at very high altitudes remain bright enough to appear. At other wavelengths, light can penetrate somewhat farther down, allowing scientists to piece together the atmosphere layer by layer, although that picture remains incomplete and often depends on how models interpret the signals received. Near the upper cloud region, temperatures are low enough for methane to condense. Tiny methane crystals form and are lifted or carried by atmospheric currents, creating bright clouds above a darker background. On Neptune, some high-altitude clouds can reflect nearly the full range of incoming visible light, causing them to appear bright white rather than blue. They drift above most of the methane that absorbs the light below, sometimes forming narrow streaks or gathering around large weather systems before changing or disappearing when atmospheric conditions are no longer favorable. On Uranus, methane clouds are also thought to form near pressures of around 1 bar, similar to the familiar atmospheric pressure at Earth's surface, although here it does not represent any kind of ground. The precise altitude and thickness of the cloud layer vary with latitude, temperature, and the amount of methane available. Some analyses suggest that methane is more strongly depleted near the polar regions, while lower latitudes may retain larger concentrations. These differences affect color, brightness, and the ability of clouds to form, while reminding us that the atmosphere is not a uniform shell surrounding the planet. Below the methane cloud layer, the composition of the clouds begins to change. Rising temperatures make methane less likely to condense, while other compounds enter conditions where they can form solid particles or liquid droplets. Infrared observations have detected signs of hydrogen sulfide near the cloud tops of both Uranus and Neptune, supporting the possibility that a cloud layer containing hydrogen sulfide ice exists at pressures of several bars. On Earth, this compound is known for its distinctive odor, but in a planetary atmosphere, its greater significance lies in what it reveals about the proportions of sulfur and nitrogen in the deeper layers. Ammonia and hydrogen sulfide can react to form ammonium hydrosulfide, reducing the amount of one or both substances remaining. Current evidence suggests that hydrogen sulfide is more abundant than ammonia in the regions that have been observed, allowing it to continue rising and form a separate cloud layer. This distribution differs from the structure commonly associated with Jupiter and Saturn, and it preserves part of the story of where the original material was gathered when the ice giants formed. Deeper still, the cloud layers become increasingly difficult to verify directly. Thermochemical models predict that regions containing ammonium hydrosulfide, ammonia, and eventually water may exist, but visible light cannot reach those depths and return. Radio and microwave signals can probe farther than ordinary light, yet their interpretation still depends on temperature, opacity, and the abundance of absorbing compounds. A cloud layer drawn clearly on a diagram has not necessarily been seen. Sometimes it simply marks the depth where a substance is expected to condense if the composition and temperature profile of the atmosphere match the model being used. What can be stated with greater confidence is that pressure rises continuously with depth. Every layer of gas must support the weight of all the material above it, forcing molecules closer together and causing collisions to occur more frequently. At first, the change can still be described in familiar units, from 1 bar to several bars, and then to tens of bars. Farther down, however, the numbers lose their intuitive meaning because no natural environment at Earth's surface allows us to experience a column of material so immense. The temperature does not remain as cold as it is at the cloud tops. In the upper atmosphere, temperature decreases with altitude and reaches extremely low values near the region above the troposphere. Parts of Uranus approach 49 Kelvin, less than 50 degrees above absolute zero. But in the opposite direction, beneath the clouds, the gas is gradually compressed and the environment becomes warmer. Heat from the deep interior, combined with the effects of compression, creates a temperature profile that rises with depth, connecting the coldest cloud tops to an interior heated to thousands of degrees. This transition occurs without a sharp boundary. There is no single moment when the blue color ends and is immediately replaced by a completely different darkness. Light weakens through repeated absorption and scattering, while thickening clouds, haze, and gas increasingly conceal the layers above. Visible wavelengths disappear first, while infrared radiation emitted by warmer matter may continue traveling through certain windows in the spectrum. To human eyes, however, the depths below would quickly become a dark realm where familiar colors no longer exist because there is not enough light to create them. Within that darkness, hydrogen and helium remain important components of the outer layers, but their density is now far removed from that of a thin gas. The average distance between particles decreases, collisions become more frequent, and compounds present in smaller amounts begin to exert a stronger influence on clouds, opacity, and chemistry. Methane, which first revealed itself most clearly by absorbing red light, gradually leaves the story of color and enters the story of matter under compression. Before reaching the region where carbon-hydrogen bonds may be broken apart more forcefully, methane passes through many changes in its distribution. Some of it condenses above, falls downward, and evaporates again when it enters warmer surroundings. Some is carried upward, where ultraviolet light can break the molecules apart and create more complex hydrocarbons, helping form thin layers of haze. The rest continues into the deeper atmosphere, mixing with hydrogen, helium, and other compounds as the pressure rises. This cycle of condensation, descent, and evaporation still belongs to atmospheric weather. It is not the diamond rain at the center of this journey. Methane crystals in the clouds and carbon crystals in the deep interior are two entirely different phenomena. One forms because of low temperatures in the upper layers. The other, if it exists, emerges under hot and intensely compressed conditions, where methane does not freeze but gradually loses its molecular structure. Thousands of kilometers of matter may separate these two regions, with pressure and temperature changing continuously along the way. As the journey continues downward, even the word atmosphere becomes less clearly defined. In the outer regions, molecules move through an environment thin enough for us to speak of winds, clouds, and weather systems. Below, density increases until the material takes on many of the properties of a dense fluid, while its composition gradually shifts toward heavier compounds. There is no single depth where the atmosphere suddenly becomes the interior. There is only a vast transition region in which the concepts that work well above slowly lose their ability to describe what is happening accurately. Gravity continues to draw every component inward, but the actual motion does not follow only one direction. Heat rising from below can cause lighter material to move upward, while cooler or denser regions sink, creating convection. Substances that condense carry latent heat as they change state, while differences in composition can either encourage or restrict movement. In some regions, matter may be mixed quite efficiently. In others, stable layering may keep materials separated for long periods. This is why a descent cannot be understood simply as a steady increase in a pressure reading. Every deeper region introduces a new environment where light travels differently, clouds have a different composition, heat is transported in another way, and chemical reactions begin to follow new paths. The upper layers tell the story of methane through blue color and cold clouds. The deeper layers prepare another story, in which methane becomes a source of carbon within a hot, dense, and constantly moving mixture. When the last traces of light have been left behind above, what remains is not empty space, but matter under ever greater compression. The temperature continues to rise, molecules draw closer together, and bonds that were stable in the atmosphere enter a realm no longer governed by everyday intuition. From here, tracing carbon toward the structure of diamond first requires an understanding of how pressure can transform matter itself, not only by squeezing it more tightly, but by rewriting the bonds that hold its atoms together. In everyday life, we usually recognize a substance by a set of fairly stable characteristics. Water can freeze, melt, or evaporate, yet it remains water. Methane can exist as a gas or freeze in the cold, but its molecules still retain one carbon atom bonded to 4 hydrogen atoms. These familiar rules create the impression that matter has a fixed identity and changes only in outward form when temperature or pressure shifts. Deep inside Uranus and Neptune, that impression is no longer entirely true. When matter is compressed until atoms are forced extremely close together, they are not simply squeezed into a smaller space. The way they interact also begins to change, because the regions occupied by electrons around each atom start to influence one another much more strongly. Bonds that were once stable can weaken, while new kinds of bonding that rarely appear under ordinary conditions may become more favorable. There is no need to imagine this as a sudden rupture. Methane does not cross a single boundary and instantly become carbon and hydrogen. The process may unfold through countless small steps as some bonds break, others form, and each new structure continues to change. In a hot, dense environment, atoms do not remain still enough to preserve one shape. They are constantly colliding, separating, and reconnecting. At first, the carbon remains inside methane, surrounded by hydrogen. As the temperature rises, atoms move more vigorously, while the immense pressure forces molecules into frequent close encounters. Through countless interactions, the carbon in one molecule may begin bonding with carbon from another. Methane gradually gives way to larger compounds, some of which may exist only briefly before breaking apart and rearranging again. The path from methane to diamond is therefore not a simple transformation. Carbon may pass through longer chains, small clusters, or regions of matter that are richer in carbon than their surroundings. Hydrogen is gradually released from some of these structures, but not necessarily all at once. The entire mixture remains in motion, heated and compressed, so each form is only one possible stage before the material moves toward another state. This also helps explain why high pressure alone does not guarantee that diamonds will form. Carbon must first be released from its old bonds, but it must also have the chance to encounter enough other carbon atoms and arrange itself into an ordered structure. If the environment is not hot enough, the atoms may not move freely enough to find the right positions. If it is too hot, a newly formed structure may be destroyed almost immediately. Diamond becomes favorable only within a certain range of conditions, where pressure, temperature, and chemical composition all support crystallization. The same element, carbon, can form very different kinds of matter. Graphite in a pencil and diamond are both made primarily of carbon, yet their atoms are arranged in different ways. In graphite, carbon forms layers that can slide past one another relatively easily. In diamond, the atoms connect in a tighter three-dimensional network, creating the material's famous hardness. High pressure can make the denser structure of diamond more favorable, but carbon still has to pass through many steps before reaching that arrangement. Water and other compounds in the planetary interior also lose their familiar properties. They may exist in states that can flow while conducting electricity far better than ordinary liquids. Under certain conditions, different parts of a water molecule may move in different ways, so the material is no longer entirely like a liquid, solid, or gas on Earth. States like these remind us that the name of a substance tells us which elements it contains, but does not guarantee that it will behave the same way everywhere. Even so, the entire interior should not be imagined as one uniform mass of strange matter. Pressure and temperature vary with depth, while the amounts of water, methane, ammonia, and hydrogen may also differ from one region to another. Each layer can therefore have its own properties. In one place, molecules may remain relatively intact. In another, they may be breaking apart continuously. Deeper still, matter may conduct electricity and move in ways that are entirely unfamiliar. Within such a complex mixture, carbon may not always be distributed evenly. Under some conditions, different components can gradually separate, much like substances that do not fully mix with one another. Regions richer in hydrogen may form on one side, while carbon becomes more concentrated elsewhere. This separation does not have to create a sharp boundary. Even a slight increase in carbon concentration makes it more likely that carbon atoms will meet and form clusters. On a small scale, each change may seem insignificant. One bond breaks, one carbon atom encounters another, and a tiny cluster forms before dissolving again. But these planets have maintained such deep conditions for billions of years. A process that is rare in a single moment can become important when repeated an immense number of times over a long enough period. This is one of the ways a planetary interior differs from a brief experiment on Earth. In the laboratory, scientists can usually sustain extreme pressure and temperature only for a very short time, yet they have still observed carbon beginning to arrange itself into diamond. Inside Uranus and Neptune, if a suitable region remains stable, matter may undergo the same kind of transformation over a vastly longer period, even if the process is slow at any given moment. Not every carbon atom will reach the same outcome. Some may remain in methane, some may enter other compounds, and some may gather into clusters that are not stable enough to become crystals. Only a fraction of those clusters may achieve the right arrangement and survive long enough to keep growing. Diamond rain, if it exists, is therefore not the simultaneous transformation of all methane, but the result of countless small processes unfolding within a mixture that is always changing. As carbon begins to separate from hydrogen, the density of different regions also changes. Lighter material may tend to remain higher, while carbon-rich matter becomes heavier and more likely to move downward. Chemistry is no longer separate from gravity. A change in the bonds between atoms can lead to the transport of material on a much larger scale, and that motion can then carry carbon into regions with new pressures and temperatures. For this reason, diamond rain is not simply a story about creating a beautiful crystal. It begins with matter reorganizing itself under unfamiliar conditions, then continues as heavier and lighter components gradually separate. From a single small methane molecule, the change can expand into a process that carries carbon through the planetary interior, transporting both matter and energy. At this depth, no diamond is yet large enough to imagine as a distinct object. Carbon is only beginning to leave its familiar bonds, gather into clusters, and explore different arrangements within an environment that never stops moving. Most of those structures may disappear almost as soon as they form, but occasionally, one cluster may become stable enough to hold its shape a little longer. It is from clusters like these that crystallization truly begins. To follow the rain back to its origin, we must narrow our view once more and focus on the journey of carbon as it leaves methane, encounters atoms like itself, and gradually enters a structure more tightly bound than any that held it before. Deep inside Uranus and Neptune, carbon does not already exist as a diamond waiting to be completed. It entered these planets long ago, when matter around the Sun was still gathering into the first worlds. Much of that carbon may have been held in methane and many other compounds, then gradually buried beneath increasingly thick layers of material, where pressure and temperature rose high enough for bonds that had remained stable above to begin changing in unfamiliar ways. We can imagine this journey beginning with a carbon atom inside a methane molecule, surrounded by 4 hydrogen atoms and held in a relatively stable structure. In the colder atmospheric layers, that molecule may drift with the currents, take part in cloud formation, or return to a gaseous state as it enters warmer regions, while the carbon remains within its original bonds. Only when methane is carried into hotter, denser regions, where the distance between molecules narrows and collisions become more frequent, does carbon's path begin to open in another direction. The change does not happen in a sudden instant, nor is there a boundary where methane immediately becomes carbon and hydrogen. Old bonds break apart in stages, while new ones form and then disappear again, causing carbon to move continuously from one structure to another. An atom that once belonged to a methane molecule may connect with carbon from a neighboring molecule, creating a larger compound while some of the hydrogen is released and mixed back into the surrounding environment. Through countless rearrangements, compounds containing greater amounts of carbon may gradually emerge. They may take the form of short chains, complex branches, or clusters that exist only briefly before breaking apart. Within the same deep region, some molecules may still retain structures close to the original methane, while others have already joined larger compounds. The process does not occur uniformly, but depends on where the material is located, the temperature it experiences, and the other substances present around it. Carbon's journey is therefore not a straight path from methane to diamond, but a continuous series of transformations in which each structure is only a temporary possibility. Carbon may enter a longer chain, leave it, and then become part of another cluster, while rising temperature and pressure gradually change, which states can survive for longer periods. Some arrangements may be possible only within a very narrow range of conditions, while others become more stable as the material continues downward. The surrounding composition makes this path even more complex. Methane does not exist alone, but is mixed with water, ammonia, hydrogen, and many other substances, so carbon is always moving through a blended environment. Some components may make it easier for carbon to separate from hydrogen, while others may keep it dispersed within the fluid for longer. This mixture makes a planetary interior very different from a simple experiment involving only 2 elements, while also opening many possible reaction pathways that may exist at the same time. Although those pathways may differ, one important trend can gradually emerge as methane continues to transform. Carbon begins forming more bonds with other carbon atoms, while hydrogen becomes less tightly attached to the new structures. The lighter hydrogen can blend into the surrounding fluid, while carbon becomes more concentrated in small regions, increasing the chance that its atoms will meet and form larger clusters. The first clusters are still extreme Most of these gatherings probably do not lead to diamond, but they are still necessary steps as carbon searches for a more stable arrangement within an environment that is always in motion. To become diamond, carbon must enter a tightly connected 3-dimensional lattice in which each atom bonds with its neighbors in a more stable order. High pressure can make this dense structure more favorable, but that does not mean the atoms automatically find the correct positions. They must still be mobile enough to rearrange themselves, while the environment must not be so hot that any newly formed order is immediately destroyed. Diamond is therefore expected to appear only within a suitable range of conditions, where pressure is high enough to favor a dense structure, yet temperature still allows the crystal to survive. If the environment is not warm enough, the atoms may not move freely enough to build a new lattice. If it is too hot, Newly formed clusters may dissolve before they have time to grow. Both factors must bring carbon into the right region, and even then, not every cluster will hold its shape long enough. Many intermediate states may therefore exist between methane and diamond. Carbon may remain in chains, disordered clusters, or regions of fluid that are richer in carbon before any crystal appears. Some structures may resemble other forms of carbon but have not yet reached the strong three-dimensional lattice of diamond. Crystallization truly begins only when a small cluster forms in the right way and survives its most unstable stage. Experiments on Earth have shown that carbon can pass through similar steps when methane or other materials rich in carbon and hydrogen are compressed and heated. In some cases, larger compounds appear first, after which carbon continues to separate and form extremely small crystals. When water or oxygen is present, the process may follow different pathways, suggesting that the complex environment inside a planet does not necessarily prevent diamond formation and may sometimes help carbon escape its old bonds more easily. A laboratory sample, however, exists only for a short time and represents only a tiny fraction of planetary conditions. Inside Uranus and Neptune, matter has spent billions of years moving through deep regions, where a carbon atom may be carried downward, brought upward, or held within the same layer long enough for slow transformations to repeat many times. Time is what allows even rare processes to accumulate into a significant result. One carbon cluster may form and dissolve, then another may appear nearby, and this sequence of transformations can continue countless times. Most structures will disappear, but occasionally a cluster may reach a size and arrangement stable enough to survive longer. Other carbon atoms can then begin attaching to its surface, allowing the structure to grow rather than dissolve back into the hot fluid around it. Not all the carbon in the planet will reach this stage. Some remains in methane or other compounds. Some enters clusters that are not stable enough, and only a certain fraction may progress toward a diamond structure. If the rain truly exists, it would not be the simultaneous transformation of all methane, but the accumulated result of many small processes taking place within suitable regions. When a carbon atom finally becomes part of a diamond lattice, it has moved far beyond the structure that once held it inside methane above. Even so, the newly formed crystal may still be far too small to see with the naked eye, and it has not yet begun to sink in the way the phrase diamond rain often suggests. Before gravity can carry it into deeper layers, the crystal must survive its most fragile stage, when even a slight change in temperature or surrounding composition could cause it to dissolve again. Only when a carbon cluster becomes stable enough to preserve its internal order does crystallization truly gain a starting point. From there, the crystal can continue to grow, drawing additional carbon from the surrounding fluid and gradually becoming a particle dense enough to begin moving downward. The rain, therefore, does not begin with falling, but with the very slow appearance of a tiny crystal seed, forming in darkness and holding its structure before any deeper motion can begin. By the end of the journey so far, carbon has escaped some of the bonds that once held it within methane and has begun gathering into small clusters. Yet there is still a difficult transition between a cluster of atoms that appears only briefly and a diamond crystal capable of continued growth. Within a hot, intensely compressed fluid, countless structures are constantly forming and dissolving because every atom is in motion and the surrounding bonds are continuously rearranging. To become the starting point of a crystal, a carbon cluster must preserve its order long enough for other atoms to attach to it. The earliest clusters may be so small that they contain only a handful of atoms. They appear when carbon atoms happen to come together in an arrangement resembling the diamond lattice, but most are not yet stable enough to survive for long. A single powerful collision or a slight change in the surrounding environment can cause a cluster to dissolve back into the fluid, returning its atoms to the chaotic motion from which they briefly emerged. This cycle of formation and disappearance may repeat countless times without leaving behind a single lasting crystal. When a cluster reaches a suitable size, the balance begins to shift. Its interior may now hold the diamond structure more securely, even while its surface remains exposed to the hot surroundings. If additional carbon reaches the cluster and attaches in the right positions, it has a greater chance of growing instead of dissolving. The size at which growth begins to outweigh disappearance is usually an extremely small threshold, yet it marks the difference between a temporary arrangement and a true crystal seed. There is no single size that applies everywhere inside the planet, because crystal nucleation depends on pressure, temperature, composition, and the local concentration of carbon. In a carbon-rich region, atoms may reach the cluster's surface more often, making continued growth easier. In a mixture that still contains too much hydrogen, carbon may remain dispersed or return to other compounds before it can join the crystal lattice. Water, oxygen, and the remaining components may also alter the reaction pathways, making some regions more favorable than others, even at similar depths. Two distinct conditions must be satisfied during this process. First, diamond must be a suitable structure for the environment, meaning that this arrangement can remain more stable than carbon dissolved in the mixture or held in another form. But stability alone is not enough. The atoms must also be able to move into the correct positions and build the lattice. A state may be favorable over the long term and still form very slowly if carbon is not mobile enough or if intermediate structures obstruct the path. This distinction helps explain why diamond may not appear immediately when pressure and temperature first enter a suitable range. Matter can sometimes remain in its previous state for a while, much as exceptionally pure water can be cooled below its freezing point without instantly turning to ice if there is no suitable place for a crystal to begin. Only when a tiny seed appears or the environment is disturbed does crystallization become more pronounced. Inside a planet, carbon must also cross this initial stage before the diamond structure can grow in a lasting way. At lower temperatures, a crystal lattice may remain relatively stable once it forms, but the atoms move more slowly and have greater difficulty rearranging themselves. At higher temperatures, carbon can move more freely, yet the order within a small cluster is also more easily destroyed. The nucleation region is therefore not simply the place with the greatest pressure or the highest temperature. It is a place where conditions reach a delicate balance. Carbon can leave its former structure, move through the fluid, and attach to a seed, while the diamond lattice remains intact despite the powerful motion around it. Inside Uranus and Neptune, these conditions probably do not lie along a thin boundary. They may extend across a substantial region where pressure and temperature change gradually with depth, while composition is mixed or layered in ways that remain poorly understood. A carbon particle carried into a favorable region by moving fluid may begin to crystallize, but if it is quickly transported into a hotter area, the young crystal may dissolve again. If it remains in place long enough, however, the seed can absorb more carbon and become increasingly difficult to destroy. Fluid motion can therefore both support and hinder crystal formation. It carries fresh carbon toward growing seeds, but it also moves particles through regions with different conditions. An upward current may carry a crystal into lower pressure, while sinking material may draw it into hotter, denser surroundings. The final outcome depends on how long the crystal remains within a stable region compared with how quickly the environment around it changes. In the laboratory, this fragile process can be observed only through signs that appear over extremely short periods. Some experiments generate pressure using powerful laser pulses, compressing a sample almost instantly before allowing it to expand again a moment later. This method can bring matter into extreme conditions very quickly, but it also gives carbon little time to rearrange itself. Other experiments hold samples under pressure for longer periods and heat them in a controlled way, allowing slower reactions more time to unfold. Because each method carries matter along a different path, the results are not always identical. A rapidly compressed sample may reach extremely high pressure before carbon has enough time to arrange itself fully, while a sample held longer may form diamond under less extreme conditions because the atoms have more time to move. The composition of the sample, the the rate of heating, and even the surrounding materials can influence the process, so the laboratory boundary for diamond formation is not a single fixed number. The crystals detected in many experiments are usually only a few nanometers across, far smaller than dust particles visible to the naked eye. At that scale, each crystal is only a tiny carbon lattice, yet it already carries the fundamental order of diamond. The appearance of these particles shows that carbon can cross the nucleation barrier during an experiment, even when the extreme environment lasts for only a tiny fraction of a second. If a similar process occurs inside a planet, the time available for crystallization would be almost impossible to compare. A seed would not need to grow quickly at every moment, because it could continue collecting carbon over immense periods, as long as it was not carried out of the stable region or dissolved again. Even so, the age of the planet does not automatically guarantee the formation of large diamonds, because convection, changing composition, and high temperatures may continually disrupt or transport the crystals. Science therefore cannot yet determine how large the particles may become inside Uranus and Neptune. They may remain mostly microscopic, or they may gather together and grow larger as they descend through carbon-rich regions. Any image of enormous diamonds goes beyond what current evidence allows, because experiments have confirmed only extremely small crystals, while their long-term growth inside a planet still depends on models. The most important point at this stage is not the final size, but the fact that a crystal seed can form within a hot, dense fluid. Once the first carbon cluster crosses the fragile threshold and begins preserving its structure, diamond rain has gained a physical starting point, even though the particle has not yet fallen any significant distance. From here, the story moves beyond how atoms may arrange themselves and toward the moment when scientists first carried this idea from calculations on paper into experiments that could be observed. After existing for decades in models and calculations, the diamond rain hypothesis was finally brought into a setting where carbon could leave a clearer trace. No one could retrieve a sample from deep inside Uranus or Neptune, since even sending a probe through their upper atmospheres would be a challenge far beyond any mission ever attempted. So instead of bringing planetary material back to Earth, scientists chose the opposite path. They took an extremely small sample on Earth and, for one brief moment, created conditions around it resembling those thought to exist far beneath the clouds of the two planets. The material they selected was not pure methane, nor was it a complex mixture containing all the water, ammonia, and hydrogen that might be present inside a planet. The research team used polystyrene, a familiar plastic made of carbon and hydrogen. Its structure is not identical to methane, but it provides the two elements most important to the process being investigated, while remaining stable enough to be manufactured into thin samples and placed inside the experimental system. Under ordinary conditions, the piece of plastic was unremarkable, but when compressed and heated intensely enough, its internal bonds could break apart, allowing carbon to separate from hydrogen and rearrange itself into a different structure. The greatest challenge was not simply creating high pressure, but keeping the sample within the necessary temperature range, even for an extremely short time. A powerful laser pulse was directed at the target's surface, causing the outer layer of material to heat up and expand rapidly. The reaction force from that expansion drove a compression wave into the sample, squeezing the material ahead of it at great speed. Rather than using only one wave, however, the researchers generated two consecutive compression waves, with the second stronger wave gradually catching up to the first. When the two waves met, the pressure inside the sample reached its highest level, while the temperature entered the range predicted to exist deep within the ice giants. This entire state lasted for only a tiny fraction of a second, far too briefly for the sample to preserve its products in the way an ordinary chemistry experiment might. If scientists had simply waited for the material to cool and then examined what remained, the structures created during compression might already have disappeared or changed as the sample returned to normal conditions. It was therefore necessary to observe the material while the reaction was still taking place. Visible light could not perform that task because the sample was trapped within a hot, dense environment and concealed by the equipment generating the pressure. Instead, the scientists used extremely bright, ultrashort X-ray pulses produced by an X-ray laser capable of recording the structure of matter over timescales of only a few tens of femtoseconds. The X-ray pulse passed through the sample at the exact moment the two compression waves overlapped, then was deflected by the atoms inside at very small angles, before reaching the detector. The way X-rays are deflected is not random when atoms have formed a crystal. In an ordered lattice, regularly repeating rows of atoms reinforce the X-rays in particular directions, creating distinctive patterns that researchers can compare with known structures. Diamond has its own characteristic arrangement, so if carbon truly crystallized, the resulting signal would differ from that of a disordered fluid or hydrocarbon chains without lasting order. When the data were recorded, diffraction patterns consistent with the diamond crystal lattice appeared. They did not represent stones that could be seen or held in the palm of a hand, but countless crystals only a few nanometers wide, far smaller than a speck of dust. Although such dimensions have almost no meaning in the world of jewelry, they were large enough to confirm that carbon had left its original structure within the polystyrene, gathered together, and formed the characteristic order of diamond while the sample remained compressed. The importance of the experiment did not lie simply in creating diamond, since artificial diamonds had already been produced by several methods. What was new was that the process had been observed directly as it happened within a mixture of carbon and hydrogen under conditions relevant to planetary interiors. Earlier experiments had found signs that carbon could transform into a denser form, but because the sample remained in its extreme state for such a short time, it was difficult to determine whether diamond formed during compression or afterward, as the material cooled. The X-ray pulse narrowed that uncertainty by recording the structure at the very moment the pressure and temperature entered the desired range. The results also suggested that separating carbon from hydrogen required more extreme conditions than some earlier experiments had implied. In the 2017 compression experiment, a clear diamond signal appeared at pressures of around 150 gigapascals, nearly 1.5 million times the atmospheric pressure at Earth's surface, and at a temperature of roughly 5,000 Kelvin. According to the models available at the time, similar conditions could exist thousands of kilometers beneath the atmospheres of Uranus and Neptune, although the precise location would still depend on how temperature and composition change inside each planet. Despite providing strong evidence, the experiment did not turn the piece of polystyrene into a miniature replica of a planetary interior. Uranus and Neptune are not made of plastic, nor do they contain only carbon and hydrogen. Water, ammonia, helium, oxygen-bearing compounds, and many heavier substances can all affect how bonds break, how quickly carbon becomes concentrated, and the range of conditions under which diamond is stable. Inside a real planet, matter is also not compressed by a wave passing through in a few billionths of a second. It remains under immense pressure for timescales covering much of the history of the solar system. That difference in time is especially important. In the laboratory, carbon had only an instant to escape its old bonds, find other carbon atoms, and build a crystal lattice, yet tiny diamond particles still manage to appear. Inside a planet, the reactions may proceed far more slowly, but the material has millions or billions of years to pass through suitable regions. This makes crystallization a compelling possibility, but it still does not reveal how large the particles would become, because convection, temperature, and surrounding composition could continually carry them into different environments. A crystal formed during the experiment also never experienced the actual rain part of the process. It had no time to sink through a fluid layer or continue collecting carbon as it descended, because the sample expanded rapidly once the compression pulse ended. The experiment mainly confirmed the first and most important step. Hydrocarbons can separate, and carbon can form diamond within a range of pressure and temperature relevant to the ice giants. The long-term movement of those crystals inside a planet must still be inferred from their density, gravity, and models of how matter circulates at great depth. The 2017 result, therefore, did not close the story. Instead, it brought the next questions into sharper focus. If diamond could form in polystyrene, what would happen when water and oxygen were added to the mixture? Two components thought to exist in large amounts inside Uranus and Neptune. Would they make it harder for carbon to crystallize? Or would they help carbon separate from hydrogen at lower pressures? And if crystals could appear in shallower regions than earlier models predicted, how broad might the diamond rain zone inside each planet be? Inside the laboratory, the tiny piece of plastic expanded and lost its extreme state almost immediately after the data were recorded, but the X-ray signal preserved the moment when carbon entered the diamond lattice. A process once inferred only from models had now left a measurable trace, clear enough to show that nature does not need an existing diamond as a starting point. With only carbon, hydrogen, pressure, heat, and an extraordinarily brief interval of time, the structure could form. The polystyrene experiment showed that carbon can enter the diamond structure under extreme conditions, but it also served as a reminder that the interiors of the ice giants are far more complex. If Uranus and Neptune are imagined as enormous mixtures under intense pressure and temperature, carbon is only one of many substances present. Water, oxygen, and other compounds may influence how bonds break, how carbon gathers, and where crystallization occurs. For that reason, after observing diamonds form from polystyrene, scientists moved in a new direction, designing experiments with compositions closer to those expected inside the planets in order to understand how water and oxygen might alter the journey from methane to diamond. The polystyrene experiment confirmed an important step. When a mixture of carbon and hydrogen is compressed and heated intensely enough, carbon can leave its original structure and arrange itself into extremely small diamond crystals. Yet that result was produced in a sample far simpler than the environment predicted inside Uranus and Neptune. The deep interiors of these planets may contain not only methane and hydrogen, but also large amounts of water, ammonia, and oxygen-bearing compounds. To move closer to real planetary conditions, scientists needed to understand how these additional components might alter the path toward crystallization. At first glance, water may seem largely unrelated to diamond formation because it supplies no additional carbon to the crystal. But within a mixture exposed to high pressure and temperature, the role of a component is not determined only by the elements it contains. Water can change the way methane melts, how molecules interact, and how hydrogen is removed from carbon-rich structures. As the surrounding environment changes, the reaction pathways change as well, allowing a process that once required extremely high pressure or temperature to begin earlier than predictions based on pure methane would suggest. To investigate this possibility, a research team used methane hydrate, a form of matter in which methane and water coexist within a solid structure. Under ordinary conditions on Earth, methane hydrate is often pictured as methane molecules trapped inside a framework of frozen water. But at pressures of tens of gigapascals, that structure becomes very different from familiar ice. The sample still brings carbon, hydrogen, and oxygen together within an extremely small space, making it a closer starting point for the composition thought to exist inside the ice giants. Rather than compressing the sample with a shock wave that lasted only an instant, this experiment placed methane hydrate between two diamond tips capable of generating immense pressure, then used a laser to heat a small region of the sample. This method allowed the material to remain under extreme conditions for longer, giving slower reactions more time to unfold, and allowing the products to be examined through several different techniques. Within the heated region, methane began to lose its original structure, forming heavier hydrocarbons while gradually releasing hydrogen as carbon continued bonding with carbon. What stood out was that diamonds appeared at lower pressures and temperatures than in many earlier experiments using only carbon and hydrogen. The signals suggested that the process could begin at around 13 gigapascals, while the favorable temperature was also substantially lower than the level required in some shock compression experiments. This does not mean that simply adding water will always make diamonds form easily. It does show, however, that water altered the chemical environment in a way that helped carbon pass through intermediate structures and move closer to the crystal lattice. Observations from the experiment suggested that methane did not transform directly into diamond as soon as the sample was heated. It first melted and began forming compounds richer in carbon, while hydrogen was released in stages. As the temperature continued to rise and the separation progressed, carbon had a chance to concentrate into regions rich enough for crystal seeds to appear. The journey still involved many of the steps predicted by earlier models, but the presence of water seemed to allow those steps to occur within a more accessible range of conditions. If these results can be applied to planetary interiors, the diamond-forming region may begin at shallower depths than previously imagined. The upper layers of the water and methane-rich fluid region, although still thousands of kilometers beneath the clouds, may already reach pressures high enough for carbon to begin separating, provided the temperature and composition are suitable. A broader crystallization zone would also give more carbon the opportunity to take part in the process, although the actual amount of diamond cannot be inferred from a single small laboratory sample. Another line of research brought oxygen into the story using a much more familiar material, PET plastic, the kind commonly used in water bottles and packaging. Unlike polystyrene, PET contains oxygen as well as carbon and hydrogen, making it a relatively simple way to observe the influence of a third element when matter is compressed by lasers. It still does not reproduce the complete mixture inside Uranus or Neptune, but it comes closer to a carbon-hydrogen-oxygen system than the earlier experiment did. When laser pulses sent compression waves through the PET, the sample was brought to pressures ranging from tens to more than 100 gigapascals, along with temperatures of several thousand Kelvin. X-rays were once again used to record how the material changed while the extreme conditions were still present. Alongside signals showing the formation of the diamond crystal lattice, the measurements also tracked the size and growth rate of the tiny particles. This revealed that the reaction not only produced carbon in diamond form, but also allowed the crystals to grow during the experiment's extremely brief duration. Compared with polystyrene, diamond formation in PET was more favorable across part of the pressure range that was tested. The researchers suggested that oxygen helped separate carbon from hydrogen, making it easier for carbon to concentrate into distinct clusters rather than remain trapped within hydrocarbon structures. One interpretation is that oxygen tends to bond with hydrogen, helping remove hydrogen from carbon-rich regions and leaving conditions more favorable for the diamond lattice to form. The process, however, should not be reduced to a single reaction in which oxygen simply removes hydrogen and diamond automatically appears. Within a hot, strongly compressed fluid, bonds are continuously forming and breaking. Water, carbon, and hydrogen may pass through many short-lived structures before becoming more clearly separated. The measurements reveal the general trend, but the individual atomic steps still need to be combined with simulations for a fuller understanding, especially because the reaction lasts for only a tiny fraction of a second. Real, 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 reale, real, real, al, el. Under suitable pressure and temperature, that water could enter electrically conductive states, unlike ordinary water, contributing to regions of fluid whose movement may be connected to the planetary magnetic field. This relationship still exists mainly within models, because the PET experiment could not reproduce the full structure and motion of a planet. Even so, it shows that diamond formation may also alter the surrounding environment left behind. Across these two lines of experimentation, one shared conclusion gradually became clearer. Carbon does not react in isolation, and the conditions for diamond formation cannot be defined by pressure and temperature alone, while chemical composition is ignored. Water may allow methane to separate and crystallize under milder conditions, while oxygen in PET also encourages carbon to separate from the hydrogen-bearing mixture. This suggests that the true interiors of Uranus and Neptune may be more favorable to diamond rain than a model based only on pure methane, although the degree of that advantage still depends on the proportion of each component and how they are distributed with depth. These results also change the way the location of the rain is understood. If carbon can begin crystallizing at lower pressures, the first crystals may appear near the upper part of the deep fluid region rather than only in areas close to the center. Once formed, they would continue passing through layers of rising pressure and temperature, where some particles might collect more carbon, while others dissolve or are carried into new regions by moving material. The rain would not begin along one fixed boundary, but could extend across a broad zone, with the rate of formation and crystal size changing according to the surrounding conditions. Even so, each experiment preserves only one part of the larger picture. Methane hydrate brings water and methane together in the same sample, but it does not contain all the ammonia, helium, and rocky material that may influence a planet. PET introduces oxygen into the system, but its original structure differs from a natural planetary mixture, and it is compressed along a very rapid path. These differences do not diminish the value of the results. Instead, they define what the experiments can demonstrate. Carbon has several pathways into the diamond structure, and the presence of oxygen, or water, may allow those pathways to open across a wider range of conditions. From this point on, the diamond rain hypothesis is no longer supported by only one material or one experimental method. Diamonds have appeared in hydrocarbons containing only carbon and hydrogen, in methane held together with water, and in material containing carbon, hydrogen, and oxygen. Each result comes from a different environment, yet all point toward the possibility that the deep interiors of the ice giants contain the ingredients needed for carbon to crystallize, perhaps not only at the greatest depths, but also in layers much shallower than originally believed. What remains is to determine where that boundary lies, not within one specific sample, but across the planet's entire map of pressure and temperature. As new models include a wider range of carbon and hydrogen proportions, and experiments hold matter under compression for longer periods, the diamond-forming region begins to appear less like a rare point and more like a broad domain. This shift carries the story into its next stage, where scientists consider whether the rain may begin earlier and closer to the outer layers than predictions maintained for decades had suggested. For a long time, diamond rain was imagined as a phenomenon that could begin only very deep inside Uranus and Neptune, where pressure had risen to its most extreme levels and carbon seemed to have almost no path left except toward denser structures. That picture was consistent with the earliest experiments, in which diamonds generally appeared only when samples were compressed with tremendous force and heated for an extremely brief moment. But as newer methods allowed matter to remain under pressure for longer periods, a process that had seemed to depend entirely on depth began to reveal another factor, slower and less obvious: the amount of time carbon is given to change. A mixture may already have entered a region where diamond is the more favorable form, yet its atoms do not immediately leave their old structures and arrange themselves into crystals. Carbon must still separate from hydrogen, gather into sufficiently concentrated clusters, and survive the fragile stage when any newly formed structure can dissolve back into the surrounding fluid. If the environment lasts for only a few billionths of a second, that entire sequence must unfold almost instantly, requiring pressure and temperature to rise to extreme levels for the reaction to finish in time. Inside a planet, however, matter is not swept through these conditions as quickly as it is in the laboratory. It may remain compressed for periods so long that even slow reactions can become part of the planet's evolution. This difference in timescale has changed the way scientists think about the depth at which the rain may begin. Instead of searching only for the place where pressure reaches its highest value, they have begun examining the entire region where carbon can gradually separate from the mixture and preserve a diamond structure long enough to continue growing. This region is not defined by a sharp boundary, because every ratio of carbon to hydrogen, every temperature, and the presence of water or oxygen can shift the path toward crystallization in a different direction. When different mixtures are modeled across a broad range of pressures and temperatures, carbon does not always remain evenly distributed throughout the fluid. Under certain conditions, the mixture tends to divide into different regions, with one part becoming richer in hydrogen, while another retains a greater concentration of carbon. This separation occurs on a small scale and does not create a clear boundary like two layers of liquid in a glass. But on a planetary scale, even a very slight tendency can gradually gather large amounts of carbon into regions more favorable for crystallization. When carbon remains diluted among too much hydrogen, its atoms have fewer opportunities to meet in the arrangements needed to form a crystal seed. Once they begin to concentrate, however, the distances between them grow smaller, carbon clusters appear more often, and the chance that one cluster will preserve its structure long enough also increases. Diamond may then form without waiting for pressure to reach its maximum, provided the environment has concentrated the carbon sufficiently, and the temperature is not so high that it destroys every newly formed order. Newer models suggest that in deep regions cool enough for the pressure present, carbon may gradually leave the fluid and enter crystals, causing the remaining material to become increasingly depleted in carbon. When the predicted temperature profiles of Uranus and Neptune are placed onto this picture, they do not pass through exactly the same region. Some models suggest that Neptune may be more favorable for carbon separation, while Uranus may lie closer to a hotter domain where the process requires a greater carbon concentration before becoming significant. This difference must still be treated as a possibility, however, because the true temperatures at those depths have never been measured directly, and every interior model carries its own limitations. While calculations have expanded the crystallization zone into different parts of the interior, experiments have shown that carbon may not require conditions as extreme as once believed. When polystyrene was held under relatively steady pressure and then heated for longer than in earlier shock compression experiments, diamonds appeared at significantly lower pressures. What changed was not only the numerical threshold, but the opportunity the material had to complete each stage: hydrogen leaving the original structure, carbon becoming concentrated, crystal seeds forming, and then beginning to grow. That interval was still brief by human standards, but for atoms it was long enough that the process no longer had to unfold within an almost instantaneous compression. This helps explain why different experiments have produced different thresholds. When a sample is driven rapidly to high pressure and released almost immediately, the reaction requires more extreme conditions to occur in time. When matter is held longer, carbon can find its way into the diamond structure under gentler compression, because time has taken over part of the role once played by enormous pressure. Inside Uranus and Neptune, time is not scarce. If a region with suitable composition, pressure, and temperature remains stable, carbon may rearrange itself countless times before a durable crystal seed finally appears. The process does not need to be fast from one moment to the next, because the planet allows small changes to repeat across millions or billions of years. For this reason, the rain may begin in shallower portions of the deep fluid region, where pressure has not reached its highest value, but matter has remained compressed long enough for carbon to complete the path toward crystallization. Here, shallower is only a relative term. These regions would still lie far beneath the clouds visible to telescopes, within an environment so hot, dark, and dense that no present-day probe could reach it. Even so, shifting the formation zone outward would significantly change the shape of the rain. If crystals appear earlier during their descent, they would have a much longer distance over which to continue growing, encounter other carbon-rich regions, or pass through layers where temperature alters their structure. Some particles may collect more carbon as they sink, gradually becoming larger and heavier, while others may be held in place by fluid currents or carried into regions where diamond is no longer stable. The rain is therefore unlikely to begin along one thin, uniform layer surrounding the planet. It probably extends across a broad region, where some areas form crystals more quickly. Others produce only small clusters, and still others prevent carbon from crystallizing even at similar depths. Experiments on Earth still cannot determine exactly where this region lies inside either planet. Polystyrene contains only carbon and hydrogen, while a real planetary interior also includes water, ammonia, helium, and many other components. The sample is also held between solid surfaces, where crystal seeds may begin more easily than they would within a fluid with no supporting surface. The newer results are therefore not a direct measurement of the depth of the rain, but evidence that the pathway toward diamond is broader than rapid compression experiments once suggested. What is gradually becoming clear is that the rain is determined not only by where the material is located, but also by how long it remains there. Pressure makes denser structures favorable. Temperature allows carbon to move, but can also destroy newly formed order. Time determines whether the slow steps between one state and another have a chance to be completed. These three factors do not act separately. Together, they open or close the pathway from methane to crystal. As this view changes, diamond is no longer confined to a deep region near the center, nor does it appear as the immediate result of reaching one particular pressure. It may begin as tiny clusters in the upper part of the fluid interior, then grow or dissolve as they are carried through different layers. Each crystal may therefore carry its own history, beginning in one place, changing in another, and continuing downward if its density remains greater than that of the surrounding material. From here, the rain begins to resemble a true planetary process. There is no boundary where diamonds suddenly appear all at once, and no brilliant layer gathering below. There is only carbon gradually leaving its former bonds, crystal seeds forming in favorable regions, and individual particles being carried deeper by gravity through a fluid that is always in motion. If the first crystals can appear earlier than predicted, the next question is no longer simply whether they form, but how they travel through the planetary interior. From a particle only a few nanometers wide, a diamond may continue to grow, combine with other particles, or sink very slowly through hot, dense currents of matter. It is at this stage that the phrase diamond rain begins to take on a more physical meaning, not as a glittering spectacle, but as the quiet settling of carbon through darkness. As the first crystals begin to form in regions shallower than earlier predictions suggested, diamond rain also starts to take on a clearer shape, although that shape is very different from what the name usually brings to mind. Inside Uranus and Neptune, there is no open sky above solid ground, nor any space thin enough for objects to fall freely like raindrops in Earth's atmosphere. If diamonds are forming there, they emerge within a hot, dense fluid, where every movement is restrained, slowed, and redirected by the surrounding material. A newly formed crystal seed may be only a few nanometers wide, thousands of times smaller than a speck of dust, and composed of just enough atoms to keep its carbon lattice from dissolving again. At that scale, it cannot yet be regarded as a separate stone falling downward. It is more like an extremely small portion of the fluid that has found a new internal order, while the entire environment around it continues to move, collide, and carry carbon from one place to another. Fluid currents may carry the crystal sideways, lift it upward, or draw it downward before gravity produces any clear motion of its own. Hotter regions tend to rise, while cooler or denser material moves downward, creating convection currents that extend across enormous distances. A tiny diamond particle caught within those currents would not follow a straight path. It would travel with the surrounding material, sometimes moving deeper and then returning to a higher region, depending on the speed of the flow and the difference in density between the particle and the fluid around it. Only as the crystal continues to collect carbon does that difference gradually become significant. Atoms dissolved within the fluid may attach to the surface of the crystal lattice, allowing the particle to grow in extremely thin layers, while other small clusters may collide with it and become part of a larger structure. This growth does not necessarily continue without interruption. The particle may pass through carbon-rich regions and then enter areas where carbon is more scarce, growing at some times and remaining almost unchanged for long periods at others. Crystals may also encounter one another within the moving fluid. If they collide gently enough and their surfaces can still form bonds, some particles may remain attached or develop into larger aggregates. Yet there is not enough evidence to know how common this process would be inside a real planet. High temperatures, powerful currents, and the complex composition of the fluid may separate the particles, wear them down, or partially dissolve them before they have a chance to become larger structures. There is therefore no firm basis for imagining a dense rain of large diamonds falling through the interior. Experiments have observed only crystals on the nanometer scale. While every stage of growth beyond that size depends on time, the rate at which carbon is supplied, and the path each particle follows. A planet may give the process billions of years, but it also places the crystals in a constantly changing environment where every period of growth can be interrupted. The word rain is therefore better understood as a process of settling rather than free fall. When a particle becomes denser than its surroundings, gravity gives it a tendency to move toward the center, but the fluid continually resists that motion. The smaller the particle, the greater the effect of drag compared with its weight, making its descent extremely slow. As the particle grows and its mass increases more rapidly than its surface area, gravity gradually becomes more dominant, allowing it to separate from the general flow and move downward at a greater speed. Even a relatively large particle, however, would not fall through empty space. It would have to push the fluid ahead of it aside continuously, creating small movements in the surrounding material and losing energy along the way. The closest familiar image may not be rain falling through air, but dense particles settling through a very thick liquid. Although the fluid inside these planets is hotter, more highly compressed, and more structurally complex than any ordinary liquid humans have ever observed. Seen from nearby, the process would probably not produce the glittering spectacle imagination tends to create. There is no visible light in the deep interior to reflect from the crystal surfaces, and the surrounding fluid may be opaque, absorbing most of the radiation passing through it. The diamonds are not cut into smooth, shining facets. They grow into shapes determined by crystallization rates, temperature, and collisions with their surroundings. Some particles may be relatively uniform, while others contain many imperfections, made of countless smaller crystalline regions joined together rather than one flawless lattice extending throughout. The downward motion would not be uniform across the entire planet. Where convection is strong, small particles may remain mixed within the fluid for a very long time before settling. In a more stable layer, where vertical motion is restricted, crystals may sink slowly but more steadily, gradually removing carbon from the region where they formed. Differences like these could make the rain stronger in some areas and extremely weak in others, even at similar depths. Over time, this settling removes some carbon from the upper region while adding denser material to deeper layers. If methane and other hydrocarbons continue supplying carbon, the process may persist for long periods. Once a region becomes depleted in carbon, however, the rate of crystal formation may decline. Diamond rain may therefore not maintain a constant intensity throughout the planet's history. It may have been stronger during earlier stages, then changed as the internal composition was gradually rearranged. A sinking crystal is also not guaranteed to preserve the same form forever. Rising pressure generally helps maintain the dense diamond structure, but temperature also increases with depth and may carry carbon into other states. In a sufficiently hot region, the crystal's surface may begin dissolving into the carbon-rich fluid, or the entire particle may transform into a state that current experiments have not yet fully described within the complex mixtures expected inside a real planet. If the diamonds retain their structure, particles formed in many different regions may continue gathering at greater depths. This possibility sometimes leads to images of a thick diamond layer surrounding the central region, but the available evidence is not sufficient to confirm that such a solid layer exists. Carbon may remain in dispersed crystals, within a carbon-rich mixture, or dissolved into other states of matter as the temperature rises. Any description of a liquid diamond ocean or enormous crystalline masses still goes beyond what experiments have demonstrated. What is more firmly supported is the continuous inward transport of carbon. Even if each particle is tiny and moves slowly, their immense numbers and the vast timescales involved could make the process important to the planet as a whole. Carbon is removed from one region, carried through another, and then accumulated or transformed at greater depth, while hydrogen and other lighter components remain above or follow their own patterns of motion. On a human timescale, the rain would appear almost motionless. A small particle might require an extremely long time to cross a significant distance, especially if convection repeatedly carries it in other directions. But for a planet that has existed for more than 4 billion years, even this slow movement provides enough time to redistribute a vast amount of carbon as long as crystal formation continues through a meaningful portion of its history. Diamond rain is therefore probably not a violent event occurring everywhere at once, but a long-lasting background process that may intensify in one region and weaken in another. Tiny seeds appear, some dissolve again, others continue growing, and particles that become dense enough gradually settle through the fluid while remaining subject to larger currents around them. There is no clear beginning and no single ending, because the rain is connected to the way the entire planetary interior cools and changes composition over time. Behind this slow motion lies an amount of energy far greater than the size of each crystal might suggest. Every particle that moves downward travels closer to the center, where gravity binds matter more strongly. During that descent, some of its gravitational energy may be transferred to the surrounding material as heat. When countless particles make this journey over millions of years, the settling becomes more than a redistribution of carbon. It may also contribute to the heat moving through the deep interior. The true shape of the rain, then, is not found in the brightness or size of the diamonds, but in the extremely gradual layering of a planet. Carbon leaves methane, crystallizes within favorable regions, and then moves downward, slowly changing the composition and energy of the fluid through which it passes. From particles almost too small to imagine, the story expands to a planetary scale, where gravity turns their silent descent into part of the way Uranus and Neptune retain, release, and transport heat throughout their long histories. When a diamond crystal begins to sink, it does more than carry carbon away from the region where it formed. It also moves into a place where gravity holds matter more tightly. That motion may be extremely slow, interrupted at times by convection currents or extended across spans of time that are difficult to imagine, but every downward interval changes the position of matter within the planet's gravitational field. The energy associated with that position does not disappear. It can gradually be transferred to the surrounding environment as heat. On Earth, an object falling from a height accelerates and then releases energy when it strikes the ground. Inside Uranus and Neptune, however, there is no open space through which diamonds can fall freely, and no surface where all motion ends in a single instant. A crystal must travel through dense fluid, continuously pushing material aside and experiencing resistance throughout its descent. The energy it loses is therefore returned little by little to the environment through small motions, collisions, and the constant disturbance of the surrounding fluid. A single particle carries only a tiny amount of energy, but the rain is not imagined as consisting of one particle alone. If carbon continuously crystallizes across a broad region, and the process persists for millions of years, countless crystals may move inward together. When these very small contributions are added across the scale of an entire planet, the settling process could become a meaningful source of heat although there is not yet enough evidence to determine how much it contributes to the total energy escaping into space. Crystallization itself may also release heat. When carbon leaves a disordered, moving mixture and enters a more ordered crystal lattice, the energy of the system changes, much as some substances release heat when they solidify. Yet the environment here is far removed from water freezing on Earth, because carbon must separate from hydrogen, pass through many intermediate structures, and crystallize within a hot fluid under immense pressure. The accompanying heat cannot be understood through a simple comparison, but it still forms part of the energy budget that planetary models must consider. Diamond formation also leaves behind another change, quieter but potentially longer lasting. As carbon is removed from the mixture and sinks, the remaining fluid becomes depleted in carbon and relatively richer in lighter components, especially hydrogen. Over time, these small changes may create compositional differences between upper and lower regions, causing the interior to become less like one uniformly mixed ocean and more like a collection of layers with different densities and properties. Such layering can directly affect the way heat moves. If hot material below becomes buoyant and rises, while cooler material above sinks to replace it, convection can transport energy outward relatively efficiently. But if composition changes with depth in a way that keeps the lower layers consistently denser than those above, that stability may resist vertical motion, like an invisible lid holding each layer close to its original position. Heat would still remain in the deep interior, but it would have to escape through slower processes. Diamond rain may therefore both release heat and alter the path that heat must follow. These two effects do not necessarily reinforce one another. Sinking crystals may warm the environment through gravitational energy, while the separation of carbon and hydrogen may also create stable layers that restrict convection and retain energy for longer periods. Depending on the original composition, the rate of crystallization, and the way matter is mixed, the same process could strengthen motion in one region while making another more still. This complexity is one reason diamond rain is sometimes discussed when Uranus and Neptune are compared. The two planets are fairly similar in size, both belong to the ice giant category, and share many of the same broad ingredients. Yet the amount of heat they release differs sharply. Neptune emits more than twice the energy it receives from the Sun, showing that its interior still supplies a powerful source of heat. Uranus also possesses internal heat, as more recent analyses have clarified, but its excess energy is only about 15% and remains far lower than that of the more distant planet. At first, this difference may seem paradoxical. Neptune lies farther from the Sun, receives less light, and has an extremely cold outer atmosphere, yet its interior transports energy into space more effectively. Uranus, meanwhile, is slightly closer to the Sun but appears thermally subdued, as though much of its energy were blocked within deeper layers. Diamond rain is considered one process that may contribute to this contrast, but it cannot stand alone as a complete explanation. Some models suggest that Neptune's deep interior may pass through a temperature range more favorable to carbon separation and crystallization, while Uranus may be slightly hotter at the same pressure, making diamonds less likely to form unless the carbon concentration is high enough. If this is correct, Neptune could receive additional heat from carbon crystallizing and then sinking, while Uranus would lack a similar contribution. Yet the internal temperature profiles have never been measured directly, so even a modest change in a model could significantly expand, narrow, or shift the crystallization region. Even if diamond rain is more active inside Neptune, the planet's heat cannot be attributed solely to sinking crystals. Both worlds retain energy left over from their formation, when matter collided, compressed, and gathered under gravity. They also continue to contract very slowly, releasing more energy as their internal structures adjust over time. Heat is carried by convection, conduction, and perhaps other processes of compositional separation, so diamond formation is only one link within a much larger system. Uranus's individual history may have made that system different from a very early stage. Its nearly horizontal rotational axis is often associated with one or more major collisions during the planet's formation, although the exact details remain unresolved. Such an event may have disrupted or reorganized the interior, allowing stable layers to form and preventing heat from escaping efficiently. If energy has remained trapped beneath long-lived stratification, the planet would emit little heat at the surface, even while its deeper interior stayed warm. Neptune may have followed a different history, one in which internal layers continued exchanging matter and energy more easily. Rising heat would sustain convection, and convection would carry methane and other carbon-bearing compounds through regions of changing pressure, allowing separation to continue. Newly formed crystals could then sink and add further energy to that movement, creating a connected cycle in which heat, chemistry, and gravity all take part, with no single factor acting completely on its own. It is also possible, however, that layering caused by sinking carbon eventually weakens convection. As the upper region becomes lighter and the lower region increasingly enriched in dense material, the interior becomes harder to overturn, causing heat to accumulate instead of escaping. It is not yet clear which effect dominates inside either planet, because the answer depends on the rate of the rain, the depth at which crystals form, and the extent to which the layers were already differentiated. What can be observed from outside is only the final result of this entire network of processes. Telescopes can measure the thermal radiation escaping into space, but they cannot directly distinguish how much comes from long-term cooling, how much from gravitational contraction, and how much may be connected to carbon crystallization. Separating these sources requires more precise measurements of gravity, temperature, atmospheric composition, and magnetic structure, along with a better understanding of how matter behaves under extreme pressure. Even though its contribution remains uncertain, diamond rain illustrates an important principle of planetary evolution. A very small change at the atomic scale can gradually influence the way a world tens of thousands of kilometers wide stores and releases energy. Carbon leaves methane, enters a crystal lattice, and is carried deeper by gravity. Every step occurs in darkness, yet together they may help shape the heat rising through layers that cannot be observed directly. As heat is released and matter begins to move, the story gradually leads to another consequence. Fluid currents do more than transport energy. In certain states, they can also conduct electricity. When conductive fluids move inside a rotating planet, the resulting electrical currents can organize themselves into a vast magnetic field, leaving a signal that can be measured from outside even though its source remains hidden deep in darkness. From the sinking diamonds, the journey therefore continues into the fluid layers where heat, electricity, and motion meet, creating the two most unusually tilted and offset magnetic fields in the solar system. Heat moving through a planetary interior does more than set matter in motion. It can also turn those movements into a signal extending millions of kilometers into space. When an electrically conductive fluid circulates inside a rotating planet, the charges within it are carried along, creating vast electrical currents. If that motion persists long enough and takes on the right structure, it can sustain a magnetic field surrounding the entire planet, even though the region generating it remains hidden far beneath clouds that no instrument can see through. On Earth, the magnetic field is often pictured as something like a bar magnet, aligned with the planet's rotational axis, with two magnetic poles located not too far from the geographic poles. That image is not entirely accurate, but it describes the most prominent part of the field around our world well enough. Jupiter and Saturn also have magnetic fields whose dominant components lie relatively close to their rotational axis, giving their large-scale field lines a more recognizable structure. Uranus and Neptune do not follow this familiar pattern. When Voyager 2 flew past Uranus, it discovered that the magnetic axis is tilted by nearly 60 degrees relative to the rotational axis, while the center of the magnetic field is displaced from the planet's center by roughly one-third of its radius. Uranus already rotates almost on its side as it travels around the Sun, and its magnetic field tilts in yet another direction, causing the region of space influenced by the planet to change dramatically during every rotation. Rather than maintaining a relatively stable structure pointing outward, the magnetosphere seems to twist and sway continuously as the planet turns. Neptune has a different geometry, but one no less unusual. Its magnetic axis is tilted by about 47 degrees relative to the rotational axis and is also significantly offset from the planet's center. As Neptune rotates, the magnetic field not only turns with it, but also changes the way it faces the stream of charged particles arriving from the Sunday. The two ice giants therefore do not possess calm, symmetrical magnetic shells. Instead, they create constantly shifting environments, as though the source of each field lies off-center within an unevenly moving layer of matter below. These measurements do not allow us to see directly where the magnetic fields are generated, but they place important limits on models of the interior. If the field-producing region were confined to a small, deep core near the planet's center, the field observed outside would generally become simpler with distance because its more complex components weaken rapidly. Voyager's detection of strong, off-center fields with many asymmetrical features suggests that their sources may lie farther outward within a layer that is relatively thin compared with the planet's full radius. In models like these, the deepest interior may be fairly stable and undergo little convection, while a layer of electrically conductive fluid above it continues to move. The convecting region does not need to occupy the entire interior. It only needs to be thick enough, conductive enough, and organized appropriately by the planet's rotation for the electrical currents within it to keep regenerating the magnetic field. When the source lies within a shell rather than a vast region extending all the way to the center, smaller and more asymmetric structures have a greater chance of surviving, producing fields more like those Voyager measured. This conductive fluid does not have to be liquid metal like the material in Earth's core. Inside Uranus and Neptune, pressure and temperature may cause water, ammonia, methane, and the products of their dissociation to carry electrical charge or allow charged particles to move through the mixture. In some deep states, water may conduct electricity as hydrogen moves through an oxygen-rich structure, while ionized methane or methane mixed with water may also increase conductivity. The entire region is probably not made of one substance, but of a complex mixture that changes with depth. The magnetic field is therefore not produced by a permanent magnet already sitting inside the planet, but by the continuous motion of electrically conductive fluid. Heat from below causes material to rise, while cooler or denser regions sink, and the planet's rotation bends and organizes these flows. As electrical charges move with the currents, they generate magnetic fields. The newly formed field then acts back upon the moving fluid, allowing the entire system to sustain itself over very long periods. Diamond rain may enter this story, but not by directly generating the magnetic field. Ordinary diamond is not the main conducting material within the dynamo layer, and small sinking crystals do not become the source of a vast planetary field. Their influence may instead lie in the way they alter the movement of the surrounding environment. Each particle carries carbon deeper, leaving behind a lighter fluid above and gradually changing the distribution of material with depth. If this process increases the density contrast between layers, some regions may become more stable and less able to convect. Hot material below may still tend to rise, but it must cross a lighter layer resting above it, limiting vertical motion. The magnetic field generating region could then be confined to a thinner shell lying between the outer atmosphere and the stable interior below. Such a geometry is consistent with models that produce complex, tilted, and asymmetric magnetic fields. Diamond rain may also strengthen motion in other regions. Dense crystals sinking downward can draw surrounding fluid with them, while hydrogen and other lighter components may move upward. This separation creates new flows of matter, adding to the motion already driven by heat. In some regions, The process may strengthen convection. In others, it may build stable layers that resist mixing. The final effect depends on the rate of crystal formation, particle size, original composition, and thermal structure of each planet. This helps explain why diamond rain cannot serve as a single answer for the magnetic fields of Uranus and Neptune. Even if carbon is crystallizing, the dynamo region is also shaped by water, ammonia, hydrogen, dissolved rocky material, and many other electrically conductive states. Rotation rate, the thickness of the convecting layer, the amount of heat flowing from within, and the collision history of each planet may all guide its magnetic field along a different path. Diamond is only one part of the network of processes arranging matter far below. Numerical models have shown that a thin convecting shell surrounding a stable region can generate magnetic fields with many features resembling the Voyager data. But a model that fits the observations does not mean the real structure has been uniquely determined. Different starting conditions can sometimes produce similar external fields, while a single flyby of each planet is not enough to track how those fields change over many years. In the case of Uranus especially, the data were gathered under a particular magnetospheric configuration, and later studies suggest that solar activity may have affected the environment during Voyager's passage, in ways that made some features appear unusually pronounced. Despite the remaining gaps, magnetic fields are still among the few ways humanity can sense motion deep inside these planets. We cannot see the conductive fluid layer, but its movement deflected the magnetic instruments aboard a spacecraft. We cannot follow the convection of water, methane, and ammonia directly, but the magnetic field carries outward clues about the location, depth, and geometry of the moving region. Each measurement made in the space above the planet therefore becomes a fragment of information about matter hidden in darkness below. Uranus and Neptune both possess unusual magnetic fields, but that does not mean their interiors are identical. The dynamo layer may be thicker in one planet and shallower in the other. Their conductive compositions may also differ, even if both are described with the same broad terms. The unequal amounts of heat escaping from them suggest that convection and internal layering have developed through separate histories. Even magnetic fields that share the same tilted, off-center appearance may therefore be sustained by different patterns of flow. If an orbiter someday reaches Uranus and measures its magnetic field over hundreds of revolutions, subtle changes in the field could help narrow down the location of the dynamo region and reveal how far the stable interior extends. Accompanying measurements of gravity and heat could help distinguish a vigorously mixed fluid layer from a stratified structure, showing how strongly diamond rain may participate in deep internal motion. A similar mission to Neptune could clarify whether its stronger internal heat is associated with a broader convecting layer. Until then, the magnetic field remains like a signal sent from layers that cannot be seen. It does not tell the entire story, but it reveals that beneath the cold blue exterior lies not a motionless mass, but electrically conductive fluids rising, sinking, and swirling under the influence of heat and gravity. Carbon may be leaving methane and settling through these currents, changing the composition without directly producing the field, while water and charged particles continue moving and sustaining the magnetosphere. From measurements made outside, the two planets appear both similar and different in ways that are difficult to separate. Both possess tilted, off-center magnetic fields, yet one world releases far more heat while the other seems to retain most of its energy within. Both may contain regions where diamonds form, but differences in temperature, composition, and stratification do not necessarily place the rain at the same depth or give it the same role. This incomplete similarity suggests that Uranus and Neptune may have followed different evolutionary paths from very early in their histories, despite forming from broadly similar materials and having sizes that are not dramatically different. Seen from a great distance, Uranus and Neptune can easily appear to be two versions of the same kind of world. Both are nearly 4 times the size of Earth. Both are surrounded by atmospheres rich in hydrogen and helium, while methane helps create the cool, gentle blue of their outer layers. Most of their mass is thought to lie within fluid regions containing water, methane, ammonia, and heavier materials, which is why both are classified as ice giants. If we considered only these shared features, it would be easy to assume that the two planets followed similar histories and still operate according to much the same internal rhythm. But the more closely they are observed, the more their outward resemblance reveals deeper differences. Uranus is slightly larger in diameter but less massive, while Neptune is smaller yet noticeably denser. One rotates with its axis nearly horizontal to its orbit, while the other maintains a less unusual orientation. Neptune releases a powerful flow of internal heat and sustains an intensely active atmosphere, while Uranus emits only a relatively small amount of excess energy. Their tilted, off-center magnetic fields make them appear similar in one respect, but even that resemblance may not arise from identical patterns of motion. Neptune's magnetic field generating region may lie at a different depth, be thicker, or conduct electricity in a different way from the corresponding region inside Uranus. The fluid layers beneath their clouds may contain broadly similar ingredients, yet their degree of mixing and their ability to transport heat do not necessarily match. These differences show that initial composition is only one part of a planet's fate. Two worlds may form from nearly the same materials, but the amount of matter they gather, the speed at which they form, the collisions they experience early on, and the way their interiors later settle into stable structures, can all send them along different paths. Over billions of years, even a small change during a planet's youth can gradually influence how heat escapes, how matter becomes layered, and where carbon has the opportunity to separate from methane. The outer solar system was not a quiet place in its early history. Bodies of matter repeatedly collided, merged, and had their orbits disturbed by the growing giant planets. Uranus and Neptune may have formed closer to the Sun than their present locations, then migrated outward as the entire planetary system rearranged itself. During that period, every major collision could alter not only a planet's surface or rotational axis, but also the way heat and heavy materials were distributed deep inside. The nearly horizontal axis of Uranus is often regarded as the trace of one or more powerful events. A large body striking the young planet could have changed its orientation dramatically, although the outcome would depend on the angle of impact and the internal structure of Uranus at the time. If the collision glanced through the outer layers, it might have transferred enough angular momentum to tilt the planet without completely mixing its deepest interior. A more direct impact could have deposited energy farther down, stirred the material, and left behind a different thermal structure. No current model explains every feature of Uranus completely, but its collision history opens an important possibility. The planet's interior may have become organized very early into layers that resist mixing. Material-rich and heavier components may have settled deeper, while lighter layers above created a density structure that remained stable. Heat from below would still tend to drive matter upward, but those currents would have to work against the established layering, like trying to stir a mixture whose separate layers continually return to their original positions. Under such conditions, convection would not necessarily disappear altogether. Weak motions could remain, heat could still pass between layers, and some regions might continue exchanging material. The difference is that energy would travel outward far more slowly than it would through a strongly mixed interior. Over billions of years, the deep regions could retain a considerable amount of heat, while the exterior emitted only a faint signal, making Uranus appear more thoroughly cooled than it truly is. Neptune may have avoided such a strongly insulating structure, or its formation history may have left behind layers more capable of convection. Hot material from the depths rises and gradually transfers energy to the regions above, while cooler matter sinks to replace it. This circulation can continue for long periods, carrying heat from the interior toward the atmosphere and eventually out into space. That energy does not directly create every wind or cloud, but it helps sustain an atmosphere with enough available energy to remain intensely active. The difference between the two planets may therefore lie more in the way energy is transported than in the amount of heat they originally possessed. Both worlds could still contain very hot interiors, but if one permits convection through most of its depth while the other is divided into stable regions, the heat visible from outside would be entirely different. A cold exterior and weak heat flow do not necessarily mean that the interior has lost all of its energy. Sometimes, they simply show that the energy remains trapped behind layers of matter that are difficult to cross. Diamond rain may contribute quietly to this layering. Carbon separates from methane, crystallizes, and sinks, adding denser material to deeper regions while leaving the fluid above relatively richer in lighter components. If this process continues across a broad region, compositional differences between the layers will gradually grow, making it more difficult for convection to overturn the entire interior as freely as before. At the same time, descending crystals release gravitational energy and may add heat to the surrounding environment. A single process can therefore alter both composition and energy, but those two effects do not necessarily lead to the same outcome. Where matter remains strongly mixed, sinking particles may add motion to the fluid and help maintain exchange between layers. Within an already stratified interior, the continued descent of carbon may instead reinforce the boundaries between regions and make it harder for heat to escape. The existing structure of each planet determines which effect becomes more important. If Neptune continues to support convection across a broad region, it may use the energy released by crystallization and sinking as a small contribution to the heat already moving outward. If Uranus was divided into stable layers early in its history, it may retain heat even if similar reactions still occur at certain depths. Diamond rain does not need to be present in one planet and absent from the other. Simply occurring within two different internal structures could produce significantly different outward effects. Temperature models also raise the possibility that carbon does not crystallize to the same degree in both worlds. At the same pressure, Neptune's deeper interior may fall within a range more favorable to stable diamond, while Uranus may be slightly hotter and keep carbon dissolved within the fluid for longer. If this is correct, Neptune's diamond rain region may be broader or more active, adding a certain amount of energy to its internal heat flow. Even so, the deep temperature profiles of these planets are inferred from models and have never been measured directly. A small change in assumptions about composition, mixing, or layer thickness could shift the crystallization region considerably. Diamond rain may be stronger on Neptune, or it may occur substantially within both planets, but current observations from the outside cannot yet determine the answer with certainty. The difference in heat cannot be attributed entirely to carbon. Energy left over from formation, slow gravitational contraction, the separation of water and other compounds, and each planet's history of collisions all contribute to its evolution. A planet does not cool through a single mechanism, but through many overlapping flows of energy, with each process becoming stronger during some periods and weaker during others. What humanity can measure today is only the outermost result of that entire history. Mass tells us how much material a planet contains, radius shows how much space that material occupies, and the magnetic field and heat flow provide clues about motion within. Yet the same collection of measurements can still be consistent with many different internal structures. A rockier planet that is strongly mixed may sometimes produce signals similar to those of a more water-rich world with deep internal layering. Diagrams that divide the interior into an atmosphere, an ice-rich layer, and a rocky core are therefore only simplified ways of helping us picture what may lie below. A real planet may not possess boundaries nearly so sharp. Rocky material may dissolve into the deep fluid, hydrogen may extend much farther downward than expected, and water, methane, and ammonia may change gradually with depth instead of occupying separate layers. Temperature and composition may not shift at the same location either, giving each region a history more complex than the colored bands shown in an illustration. The fact that Uranus and Neptune are not completely alike actually becomes an advantage for science. If the solar system contained only one ice giant, many different interior models might remain equally acceptable. Having two worlds similar in size, but clearly different in density, axial tilt, and heat flow forces every model to explain not only their present structures, but also the paths that cause them to diverge. That comparison extends beyond the solar system, where planets with sizes between Earth and Neptune appear to be fairly common. Some worlds may be rich in water, some may possess extremely thick gaseous envelopes, while others contain much larger proportions of rock or carbon. Although Uranus and Neptune cannot serve as templates for all of them, they remain the two nearest places where humanity can test ideas about how medium-sized planets form, cool, and distribute their material. Across those countless distant worlds, carbon may follow many different paths. Where conditions are too hot, it may remain dissolved in fluid or continue to exist within other compounds. Inside a planet cool enough and under suitable pressure, carbon may crystallize and sink, gradually rearranging the entire interior. Diamond rain may not be a strange process limited to the two blue planets of our own system, but one of many transformations that can occur in worlds rich in carbon and hydrogen. Even as its broader significance becomes clearer, the closest questions remain unanswered. No one knows how many major collisions Uranus experienced, which parts of its interior still convect, or the true ratio of water to rock inside either planet. The depth of the magnetic field generating region, the location where carbon begins to crystallize, and the amount of heat diamond rain may produce also continue to vary from one model to another. Their outward resemblance ultimately leads not to a simple answer, but to a deeper appreciation of history. Two planets may begin with nearly the same materials, yet a collision at a different angle, a longer period of gathering matter, or an internal layer that formed slightly earlier can alter the way they cool for billions of years afterward. Their atmospheres, heat flows, magnetic fields, and deep internal rain all carry traces of those early differences, even though from afar the two worlds still appear as a closely matched blue pair. By this point, diamond rain no longer stands alone as an unusual phenomenon. It has become part of the larger story of planetary evolution. It connects the carbon and methane to internal layering, links unimaginably small crystals to the heat flow of a world tens of thousands of kilometers wide, and joins brief experiments on Earth with processes that may continue for billions of years. What we know is enough to show that diamonds can form under conditions relevant to the interiors of ice giants. What remains uncertain is the scale, depth, rate, and true influence of the rain inside each world. The final part of the journey will return to that boundary, where experimental evidence ends, models begin to reach farther, and unanswered questions await a new mission into the outer solar system. After passing through blue clouds, hot fluid regions, methane bonds gradually breaking apart, and carbon crystals that may be settling through darkness, diamond rain now seems closer than it did at the beginning of this journey. It is no longer merely a beautiful image associated with two distant planets, because many parts of the process have been tested through physics, simulations, and experiments. Even so, the distance between a nanometer-scale crystal in a laboratory and a rain lasting billions of years inside a planet remains immense, and that distance defines the most honest boundary of what science can currently say. The most certain part begins with the two planets humanity has observed. The masses, sizes, atmospheres, and magnetic fields of Uranus and Neptune have all been measured, although not with equal precision. Light emerging from their upper layers reveals the presence of methane and its contribution to their blue color. Thermal radiation shows that their interiors are still exchanging energy with space, while their gravitational and magnetic fields carry indirect traces of the material hidden below. None of these measurements reveals diamonds, but together they confirm that the planets contain environments hot, dense, and complex enough that methane cannot be treated as a gas, retaining the same form from the clouds all the way to the center. Even the broad internal structures of these worlds are understood by working backward from external observations. Their masses, many times greater than Earth's yet smaller than those of the gas giants, indicate that their interiors must contain substantial amounts of water, methane, ammonia, rock, and other heavy material. There is no clearly defined solid surface beneath the clouds. Instead, the atmosphere gradually blends into intensely compressed fluid regions, where temperature rises with depth. Individual models may arrange these components somewhat differently, but they all lead to the same general conclusion. The matter inside does not exist in the familiar states encountered under ordinary conditions on Earth. The next layer of evidence comes from the laboratory, where a very small part of the process has actually unfolded in front of scientific instruments. Materials containing carbon and hydrogen have been compressed, heated, and observed with X-rays, producing signals from extremely small diamond crystals. When water or oxygen was added to the mixture, the pathway for carbon separation remained open across different ranges of conditions, sometimes at lower pressures than in experiments containing only carbon and hydrogen. These results are no longer merely speculation about whether diamonds might appear. They show that carbon can truly separate from hydrogen and enter a crystal lattice under pressures and temperatures relevant to the interiors of ice giants. Certainty extends only that far. An experiment can record diamond as it forms, but it cannot follow that particle through thousands of kilometers of fluid, nor can it keep a sample under planetary conditions for millions of years. The crystal's final size, the speed at which they sink, the amount of carbon involved, and the way convection carries them through different regions have never been measured directly. Even the location where the rain begins changes according to the composition and temperature profile chosen for each model. The crystals may remain mostly extremely small, continuously forming and dissolving within the fluid. They may also grow as they sink through regions richer in carbon, collide with one another, and form larger particles. Farther down, increasing temperature may alter some crystals or dissolve them back into another state of carbon. No current evidence allows us to state with confidence that a solid diamond layer, an ocean of liquid carbon, or enormous crystalline masses exist around the core, even though such images often appear in more imaginative descriptions of the phenomenon. A more physically reasonable picture is a long-lasting process of precipitation, in which carbon gradually leaves the mixture and moves inward. Each particle may be tiny, and every stage of its descent may be slow, but planetary time is long enough for these small movements to accumulate into a large-scale redistribution of matter. The upper regions gradually become depleted in carbon, the deeper layers receive more dense material, and hydrogen and other lighter components continue to follow their own patterns of motion. These compositional changes may influence convection, although the direction and magnitude of that influence remain uncertain. The heat associated with the rain lies within a similar region of uncertainty. Carbon crystallization may release energy, while particles descending farther through the gravitational field may transfer additional heat to the surrounding fluid. Over millions or billions of years, the total energy could become significant, especially if the diamond-forming zone is broad and a large amount of carbon takes part. Yet no measurement has isolated this heat from the energy left over from planetary formation, slow gravitational contraction, and other processes of internal separation occurring at the same time. The contrast between Uranus and Neptune makes the question more compelling, but not simpler. Neptune releases a strong flow of internal heat, while Uranus emits only a relatively small amount of excess energy. Diamond rain may occur more readily within part of Neptune's interior, or Uranus may trap heat beneath stable layers. Both possibilities are consistent with some of the available evidence, but neither is enough to make carbon the sole cause of a difference that may have existed since very early in the histories of the two worlds. Their magnetic fields offer another indirect window, but they cannot reveal exactly where the rain occurs. Both fields are sharply tilted and offset from the planetary centers, suggesting that they are generated within layers of electrically conductive fluid located some distance from the center. Water, ammonia, hydrogen, and ionized components may all help sustain those electrical currents. Diamond does not generate the magnetic field directly, but sinking carbon may alter how the fluid convects or becomes stratified, indirectly affecting the region where the field is produced. This connection still remains within models, where even a small change in internal structure can significantly alter the result observed outside. The remaining gaps do not exist because science lacks ideas, but because humanity has so little close-range data. Voyager 2 flew past Uranus in 1986 and Neptune in 1989, collecting only brief snapshots before continuing beyond the planetary region. The spacecraft did not remain long enough to observe their magnetic fields over many seasons, fly past them from enough angles to create detailed gravity maps, or release probes capable of descending through their atmospheres. In the decades since, telescopes on Earth and in space have continued observing their clouds, atmospheres, thermal emission, and seasonal changes, but light still returns information only from relatively shallow layers. Everything deeper must be reconstructed from the effects it produces outside, like trying to understand motion beneath murky water by watching the ripples on its surface. Each new measurement can eliminate some models, yet many different internal structures remain capable of producing similar external signals. An orbiter could change this situation by remaining near one planet for years, measuring its gravitational and magnetic fields from many locations, monitoring its heat flow and atmosphere over time, and sending a probe deep enough to determine the composition of the outer layers. Such data would not allow us to watch a diamond crystal falling directly, but they would greatly narrow the possible temperatures, densities, and compositional ratios within the interior. From there, scientists could determine how broad the crystallization region might be, and whether the rain is likely to have a strong or limited influence. The Uranus orbiter and probe concept was given high priority in this decade's planetary science strategy, precisely because such a mission could answer many questions at once. Uranus is not only an unusually tilted planet, but also the nearest representative of a class of worlds whose sizes are common beyond the solar system. Understanding its interior, atmosphere, and magnetic field would help explain not only carbon rain, but also how medium-sized planets form and change over time. Neptune remains farther away, and no equivalent mission has yet been selected for launch, even though the differences between the two planets make returning to both especially valuable. Detailed measurements at Uranus could eliminate many models, but only by comparing them with similar data from Neptune could science determine which features belong broadly to ice giants and which are products of each planet's individual history. The immense distance and long travel time mean that a return cannot happen quickly, so many of today's questions may remain unanswered for years to come. While those missions remain in the future, laboratory research can continue moving the story forward one step at a time. Mixtures more closely resembling planetary compositions can be compressed for longer periods, temperatures can be controlled more precisely, and crystal nucleation can be observed at multiple stages. Simulations can also be expanded to include more atoms, allowing carbon separation to be followed across longer timescales. Each improvement will narrow the unknown, although no experiment on Earth can ever fully replace data gathered from a real world. Looking back across the entire journey, Diamond Rain lies between three levels of understanding. We know that these two planets contain methane and regions of matter under immense pressure. We have seen carbon crystallize into nanodiamonds inside samples brought to relevant conditions. But where those crystals exist, how abundant they are, and how they may have changed Uranus and Neptune still belong to the realm of scientific inference. That incomplete understanding does not make the phenomenon less meaningful. Instead, it shows how science often reaches places that cannot be observed directly by connecting many small traces. An X-ray pattern in a laboratory, a tilted magnetic field measured over a few brief hours, a faint flow of heat escaping from a planet, and a model of carbon under compression are all separate pieces. Placed together, They create a possibility strong enough to investigate, while still leaving gaps that must be respected. From billions of kilometers away, Uranus and Neptune continue to look almost unchanged. Their blue color still conceals the deeper layers, while the atmosphere moves above an interior humanity has never touched. Far below, methane may be gradually losing its structure. Carbon may be gathering into tiny crystal lattices, and individual particles may be quietly descending through hot, dense fluid. There is no light to make them sparkle and no sound to mark the distance they travel. There are only gravity, heat, and time continuing their work, so slowly that no human lifetime could perceive it, yet long enough to rearrange an entire planet. Thank you for joining Sleep Gravity on this journey, from the blue clouds of the outer solar system to the depths where carbon may crystallize in darkness. As Uranus and Neptune continue along their vast orbits, the rain deep within them remains suspended between what has been demonstrated and what still waits to be seen, quietly reminding us that even the worlds that seem most still may be changing in places sunlight will never reach.